you know. We have Robbie here to talk to us about eliminating die solder with pinpoint accuracy using simulations. So Robbie has dedicated his last 20 years of his career to R&D, simulation, and metal forming technologies. He holds a bachelor's degree in mechanical engineering from the University of Waterloo and a master's degree in science from the University of Toronto. He joined the R&D team at Exco Engineering in 1997. He's focused on understanding the impact of experimental work on die cooling, which led to the development of automatic temperature control system, a novel way of cooling core pins, which is safer than jet cooling. In 2007, he joined the Magna R&D group and explored the castability of large structural automotive products from both experimental and theoretical perspective, and various casting methods ranging from semi-solid, high-pressure die casting, and low-pressure prone mold casting. And then in 2012, he formed the company Bolster Technologies, where the core mission was to bring die casting to a more predictable science. And they specialize in supporting die casters in runner and gate designs backed by simulations, as well as supporting die casters in increasing productivity and casting quality with proper thermal die management. So like all the presentation, we'll have about 20 minutes to go through the presentation, and then at the end we'll have a question and answer period. So please welcome Robbie.
Thank you. Can you hear me? A little bit about the background on this project. It was inspired by the Director of Advanced Engineering at Gibbs Die Casting. And if any of you know Gus Mueller, you know he's notorious for pushing boundaries and challenging limits. And in this particular case, it's about challenging the limits of cycle time on a heavy, thick wall casting that is plagued with die solder problems. So that's the background of this. So I want to thank Gus Mueller and Gibbs for giving us the opportunity to study this in a scientific way and to correlate our simulations with reality. So, as for the problem, I don't think anybody who's been exposed to any amount of die casting, these images are not new to you. Aluminum welds to the die steel and stops you from running and making parts and affects productivity. Nothing new, and of course it affects the casting by tearing off the skin and causing scrap rates. So these are just some visual examples of die solder, which is a problem that we look to address. And die solder, of course, causes all kinds of failures at the production cell, parts sticking to the die, scrap rates due to leakers and surface defects, and downtime because you have to stop the die to remove these stuck castings, and to stop it occasionally to polish the cores and remove any small amount of solder. So ultimately, the die solder causes a significant problem for die casters in regard to productivity. And if American die casters want to be productive and competitive on a global landscape, they have to address this problem in a more scientific way. And that's the mission and focus of this project. Just a brief review. I'm not going to go into a lot of details on the literature of die solder, but I think everyone, all the papers that we reviewed, you can see that the cast alloy actually bonds and forms a chemical bond with the die steel, and it stays there, and it's very difficult to remove it. When it starts, it's very difficult to manage it. And most of the researchers agree that the process that leads to die solder, the conditions are the degradation of the protective layer, the die loop, And some may or may not agree with this particular condition, but they all overwhelmingly agree that if the die steel operates at an elevated temperature, you will have solder. And so we wanted to find out if we could use simulation to predict precisely what kind of cooling design is required and be confident that those designs will work in the foundry. We found literature by some researchers at Oak Ridge National Labs, and these guys did an excellent experiment in which they dumped a steel core into a bath of aluminum. And these experiments have been done before. You dip the core in the aluminum and then you do microstructure tests and you can see the intermetallics. But what's unique about their test is they place a thermocouple inside the core, right at the surface, so you can precisely measure what is the core temperature during immersion. And they would remove this core and re-immerse it back at various set point temperatures of the steel to figure out what is the precise temperature at which, when aluminum is exposed to steel, what is that temperature that it solders. And one thing that was very interesting about this work, the melting range of aluminum is, the solidus temperature is about 926 Fahrenheit to 1065. And they've noticed that even if the die steel exceeds the melting temperature of the alloy, when exposed to the melt, it still does not solder. And they found a very precise temperature range, in the range of about 1022 to 1054. And this is perfect for a simulation, because when you have a simulation of that gassing process with the liquid metal contacting the steel, you can track the surface temperature increase and compare this threshold to identify the exact areas that would solder. And so we tested these, the results of this, because their results clearly identify what is the solder temperature range. And simulation tools are fully capable of capturing all of the modes of heat transfer in the die casting process and predicting steel temperature during the solidification phase and the effect of the cooling channel. So there is absolutely no reason why a simulation tool cannot, with confidence, predict what feature will solder. So the objective of this project was to use simulation tools to find a cooling design that could speed up productivity by more than 20% for this thick, heavy wall casting that I just mentioned, and eliminate downtime due to solder, and to see if we can do that on paper and test it in the foundry and confirm that we can do that ahead of time and not be reactive in the process. So the methodology we use, Gibbs die casting had this heavy wall part, and they had a limit of how fast they could run this part without having a solder problem. So they had that in the foundry data. We used our simulation to replicate the exact process in the virtual world, and then we compare the simulation results with the actual solder location observed. Then we simulate this existing die at the new target desired cycle time to find out new features that would solder. And then revise the cooling design to address these features and validate it, test it in the simulation, and see if we can actually build this die in the foundry and if it actually will perform as predicted. So the case that was investigated here is this, it's almost like a brick, a very sturdy, heavy, thick wall part with some deep metal sabers. That's mounted in a powertrain system that's over 700 horsepower, so it's a very, it has to be very sturdy, very stiff, and because of that it has a lot of very thick sections on the part. And mind you, for this particular part, the maximum, the fastest cycle time was 97 seconds. And that's in spite of all of these cooling passage drilled in that die to address solder. And it was still not possible to achieve a faster cycle than 97 seconds cycle time. So we decided to simulate the Foundry settings, and this is just a summary of the general simulation settings that was used. And all of the die steel components were accounted for. All of the cooling passage, even the ejector pins, the shot sleeve, plunger tip was all accounted for. And this is just some examples of the type of simulation results that was achieved. This is the steel temperature increase during dwell. This time is the time after shot. So this is the dwell time. And it identified very local, precise features that exceeded a certain threshold that we can use to compare with the research findings to determine if simulation can actually predict die solder. And we also use some of these visualization tools to rotate the die and identify features within the steel. And you can see which feature or which core, how these cooling passages are addressing some of the hot spots as an example. So it's a very great visualization tool that pretty much tells us what are the features that needs to be addressed. As a summary of the results, after running 20 casting cycles to reach steady state for the baseline cooling at the maximum cycle time, at the fastest cycle time achievable in the Foundry, we looked at the steel temperature on the cavity during dwell, and we noticed that the steel reaches a peak temperature after about 9 seconds for this particular part. So the temperature increase, it reaches a maximum somewhere in 9 seconds. The total solidification time was 25 seconds. 9 seconds about the peak, and then it tapers off. So we're able to capture that peak temperature both on the physical location and temporarily within the solidification phase of the casting process. And we actually got 100% correlation with this, with those lab tests that done at Oak Ridge National Lab. We actually set the bar, the threshold slightly lower to make sure we don't miss any solder features, because we are actually investing, Gibbs was investing money in physically building the die and testing it. So we wanted to make sure we capture every feature. And we noticed that it is surprisingly few features. And one of the things you can learn from just this visual display of the simulation results is there's no need to overcool an entire die to address few tiny, very local features and solders. And as an example, and these are just the same images of the ejector die, and this core here, I thought this was very interesting. This is a huge bubbler that was physically positioned on the baseline cooling design to address solder, and it still had a solder problem, which is also predicted by the simulation, correlated with the physical location in the Foundry. As an example, that we could have seen this if we know just this one magic number from those research. So the next step of the process was to remove 20 seconds out of the cycle time, which turned out to be 21% faster. What actually surprised me again was it didn't go out of control thermally. There was just a few additional areas. Some of them were threatening to reach that threshold, and after speeding up by removing 20 seconds off the cycle time, just make those areas more exaggerated, and a few additional areas lit up. Very few, actually, only with 2 more features. And so this gives us the perfect opportunity to address those very local features of the die cavity. And in this particular case, this large insert existed, so it was very unnecessary to 3D print this entire large core. So we wanted to be creative to test different cooling strategies. And in this particular case, we tried, what if we have a copper sleeve, drill a cooling passage in the back, and have a close tolerance so that we can address the actual feature that the simulation pretty much bellows and say, here is where you need to address. We use a high temperature thermally conductive paste, Omega Therm 201, I think it was. And we tested this in our simulation to see if it worked, and you'll see in a couple slides later. So this is how we address the need for additional cooling on the cover and ejector side. And close-up of that design in all of these features. And there are some other features, for example, that large core that actually soldered even with that big bubbler tube that was positioned there. It called for conformal cooling, so we designed a conformal cooling passage in those features. And on the top slide, there's a couple of areas where when you have these square corner die steel, the edges solder. So putting a cooling in the middle really doesn't help you because the corners where you have aluminum surrounding these corners of steel, they really are the features that actually solder. So conformal cooling is the best way to get to those locations. So so the results of this, this is with the copper inserts, by the way. The simulations show it didn't overwhelmingly cool those features, but it cooled it just enough to be below that threshold of 1,000 degrees Fahrenheit. So we really have to trust that research data as we built this die. So this is the original cooling. That's the effect of those copper sleeve inserts cooled from the back. And you can see a close-up here of the copper is, of course, cooled. And we applied a heat transfer coefficient here. There was some experimental measurement in the range of about 2 to 2,000 watts per meter squared K was the heat transfer coefficient that accounted for the Omega Therm paste. And you can see in the previous original case, there was a cooling passage gotten close, but it still wasn't enough to get to those, but the copper sleeves did. And you can see the ejector die, we have an improvement from the baseline, but it wasn't overwhelmingly cool those areas, but it was just enough to drop below that threshold temperature. And the covered ejector, another interesting thing here is that we did not actually change the cooling in this feature, but because conformal cool was applied here, and this feature butts up to this location, it removed the heat load that was imposed in this area and caused it to operate at a lower temperature, which is really interesting. So if you have a feature that solders on one half of the die, you can attack it from an accessible side of the opposite end. And this gets demonstrated in the simulation. So in summary, after all of those trials and revision of cooling, we actually built that die and tested it in the Foundry, and it actually ran for before with the baseline cooling at the 97-second cycle time. Every 4 hours they had to stop, polish the cores, and in order to maintain this somewhat steady process. And just by applying this strategy and those threshold temperatures, we're able to achieve, figure out a design on paper that worked with zero downtime due to die solder, and they ran over 5 hours consecutively. And using, there's a lot of research paper that's used, but there's kind of a gap between the industry reading those and applying it to the real world. So this is an example of the fundamental research can be can help die casters be much more productive in the case of die solder. So in conclusion, of course, simulation was able to predict 100% of the die features of solder when we use that threshold temperature of about 1,000 degrees Fahrenheit exposed to aluminum during well. And notice that it was about 1,022 to 1,050 in the experimental results. We attributed that discrepancy, that small discrepancy, to it was just a dump test that determined the solder threshold. But in high pressure die casting, you have thousands of PSIs of pressure that's forcing the aluminum to be more intimately contacting with the steel, and thereby accelerating the rate of diffusion is the most likely explanation of why it actually solders in the foundry at a lower temperature than those measured. And so, yeah, so we're very happy with this methodology. We can accurately predict die casting, and therefore when you're quoting a new program, building a new die, and you have a target of desired cycle time, this is a criteria that can be used to be confident of what your desired cycle time is, that you can achieve this and minimize downtime and scrap rate. And ultimately, American die casters need to improve their productivity if they're to be competitive on the global landscape. So, thank you.
Do we have some questions? Okay. It's going to be tossed this time now. Ready for it?
Okay. In your data search, did you have data on some of the low iron alloys as well as regular, conventional 380? See if there's a difference in that temperature range between soldering and no soldering?
Yeah, in this particular case, actually, it was only A380 alloy. So we used the research findings of A380 alloy. One interesting thing was that they seemed to propose or theorize that die solder happens if the temperature is above the dendrite coherency temperature. And that makes sense because if you have too much solid fraction, it prevents the diffusion of the liquid onto the steel. And if you look at the time scale for diffusion, solid diffusion, it's in the range of hours or tens of hours. So therefore, you do need a liquid phase in contact with the steel. So it appears as though the solder threshold is related to the dendrite coherency point, and therefore the alloy composition can determine that. That would be an interesting research topic.
Thank you. That's good.
Okay.
When you inserted the copper tube, how close to the surface did you get when the cooling?
Oh, sorry, I missed that question.
So when you insert the copper tubing into from the backside, okay, right, did you put water in it? How close did you get that to the surface of the H13 tool seal on the outside?
That's correct.
I haven't measured that, but it's in the order of about 3 millimeters, something like that, to the 3 to 4 millimeters distance to the cavity.
And as a follow-up, was that a new insert you did that with also then, or was one you had worked on and polished with before?
It was a new piece.
New piece, so it was so the copper was a whole new piece then, so we started a new baseline then, okay.
And to answer his point a little more, the reason why we put the copper sleeves, that we...
Hang on.
Just to help me answer, the reason why we use the copper sleeves, that we get extremely close to the steel and for safety, we don't want to crack. That's why we had the sleeve built in that got extremely close.
Keep the water away, keep the water back.
Keep the water away, correct. We did get much closer than we were comfortable with the 3 millimeter range, but we had no problem.
What kind of tolerance you have between copper and steel?
That's proprietary.
And what kind of coating did you put on it to make it stick? That's right, yeah, all that stuff. Right back here.
So usually it's accepted that soldering is at least somewhat dependent on fluid velocity during the filling. Was this a low velocity filling process, or is there any intention to look at sensitivity of filling velocity in these areas?
We actually exclusively just rely on temperature during dwell. There might be a higher chance of soldering close to the gate. And I question if it's because of lube washout, because during the shot, if you have high-speed aluminum impacting an extended surface, there's massive convective heat transfer from that liquid metal to the steel, which I haven't heard any accounting of that being attributed to die solder, which may be one mechanism as well.
And as a follow-up, did you keep all the rest of the process parameters the same? So did you keep the gate velocity, the pressures, all that stuff all the same? How about spray? Did spray stay the same then?
No, we actually reduced the dwell
Okay.
time.
So you just reduced the dwell time, that's where you get the cycle
Yeah,
time
that's
saving
what
at
we
that. So did you reduce the spray also?
Spray in.
Okay, so that's where the cycle time came, same, okay, so, okay, good. All right.
Everything else was the same.
Same, okay.
Questions?
Did you consider any differences in the heat transfer coefficient of the omega therm, maybe try lithium grease or something of that nature? That was actually, there might be some data in some of the NADCA archives from work that was done years back. I just wondered if you could consider that in a simulation.
Yeah, actually I did. I did this personally because I was uncomfortable with the idea of relying exclusively on this perfect contact between the aluminum, between the steel and the copper. So I tested, and there's much research on solid-solid contact heat transfer coefficient of just two copper pressed onto a steel surface. And actually we ran that simulation with just a dry contact, if you will, and it still had predicted a threshold below that number. So that gave me confidence that, yeah, we can build this, and it should work.
Other questions? Got a couple minutes, you need something else? Okay, great. Thank you very much, I appreciate it. We've got a couple minutes here.